So I'm really excited to welcome Kirsten Siebach today to give our colloquium. And Kirsten is at Rice University, where she's an assistant professor, and she is a Martian geologist. So she studies source to sink sedimentary processes on Mars and the early Earth, and to help us understand the history of water and surface environments in our solar system. And in addition to this research, Kirsten is on the science teams and the operation teams for several Mars rovers, including MSL, or the Curiosity rover. And she was also involved with the Phoenix lander and 2 Mars exploration rovers. And she started all this as an undergrad at WashU St. Louis before doing a PhD in geology at Caltech with John Grotzinger. And in fact, we were friends at Caltech, and this is how I know she's going to give such a great talk, because I've seen her give talks before. And she did her postdoc with Scott McLennan at Stony Brook. And another thing that I think you guys will all be interested in is that Kirsten's really passionate about science outreach, which is something we've been discussing a lot as a department. And yeah, always has a fully booked schedule of talks. So we're lucky to have her here today to talk about source to sink processes in Gale crater, investigating sedimentary rocks on the red planet. Thanks, Kirsten.
Thanks, Megan. It's great to be here. And let me just get this sharing. Okay. All right, there we go. All right. Well, thanks so much for the invitation. It's really fun to get to come virtually and get to meet a whole lot of different people and speak to different departments. And so I'm always curious what you'll think of this. So I'll be listening for your questions. But I'm excited to tell you about kind of this big picture of source to sink processes in Gale crater and what we've been finding with the Curiosity rover. I always want to start by thanking my collaborators, and that includes a really wide range of people, because when we're working with the rover team, you need every kind of engineers, experts on every instrument, experts on atmospheric science, geochemical science, mineralogical science, sedimentology to work together. So we always have this kind of wide range of different people, but working on this interdisciplinary team has definitely shaped what the rover has done, what observations we have, and also our interpretations and our understanding. And so just really grateful for the broader team, as well as specifically for collaborators who have worked with me on these projects and advised me on these projects. And special thanks to my lab group. And we'll talk a bit about the work from Dr. Thorpe and Dr. Pyre, who are postdocs in my lab group. When you are working with this kind of team, we actually have around 400 scientists around the world that are somehow involved in the science and operations team, but closer to 150 that are kind of more involved in science and operations of the rover on Mars. And this is the group at one of our semi-annual team meetings. And we just had a team meeting over the last 2 days. And so it was kind of fun to be able to go to that and come here to talk to you, because we can do this all virtually. But when you're working with a team like this, you frequently end up with slides that are something like this. And this is when we're actually operating Curiosity. And in this case, we had some wheel issues, and we were trying to determine what would be the best path from A to B to keep the wheel safe and also to see kind of key geological features. And in this case, we asked 5 different route planners, what the ideal path would be. And you can see that there are about 8 different paths. Without any roads, with 400 people to drive one mission. It's almost always a game of compromise and communication to explain why any given path is the right one, right? You can actually see that one of them doesn't even go to point B. So there's a lot of compromise and discussion involved in this work. And so I'm just grateful to work with this team. It is really fun. After all the compromise and discussion, you have a lot of people that really care about what this rover has found. And that's always been really exciting. Okay, so starting from kind of big picture, thinking about Mars, right? We're a 4th planet from the sun. It's cold, barren today. There's no magnetic field. There's never been any plate tectonics. The atmosphere today is about 6 millibars, so something like 0.6% of the atmospheric pressure that we experience on Earth. And that causes just a tiny amount of a greenhouse effect, but really also kind of gets blown around rapidly in kind of significant wind storms, just because the temperature differences between day and night are on the order of 100 degrees Celsius. And so Mars today seems like a pretty foreign environment where you're mostly going to be looking in terms of sedimentary processes. You can really only think about aeolian processes in comparison to Earth. However, 4 billion years ago or 3.5 billion years ago, when we think life started on Earth, Earth and Mars may have looked much more similar. So Mars had a magnetic field only briefly, probably before 4 billion years ago, and it never developed plate tectonics. But at that time, 3.5 to 4 billion years ago, we're not actually sure if Earth had developed plate tectonics. And what we do know is that despite the sun being less bright, both planets had liquid water and environments that would have been habitable for Earth-like life, and potentially environments where life could have originated. And so Mars gives us kind of a really good sense of, what this time period was like. And the reason for that is because on Earth, right, if you just kind of look at it, this is just a timeline of Earth and Mars through time. So 4.5 billion years ago, Earth and Mars formed. You slide down the timeline to the right, you get to today. On Earth, we are interested in this time when we think life started, probably around between 3 and 4 billion years ago. But because of plate tectonics, because of life changing the way that geologic systems operate, changing the atmosphere, et cetera, most of Earth's surface is preserving about the last billion years of time on Earth. And we're only preserving a few percent of the crust from the Archean, right, from that time when life may have started. On Mars, we can argue that that time may have actually looked kind of similar, but we actually have a much better sedimentary record preserving that time period. And so because Mars kind of dried up, the last 3 billion years or something or so are pretty dry. They had a couple of kind of flood events, a couple of volcanic events, right? But for the most part, you didn't have water flushing across the surface. You didn't have life changing it. And so you preserved really well this time period between 3 and 4 billion years ago. And on a large scale, the features that we see, we use craters to kind of date different surfaces, right? If it's completely saturated in craters, it's probably 4 billion years or 4.2 billion years or older. Whereas if it has slightly fewer craters than that, it can tell you it's relatively younger. Based on that, we can, and spectroscopy, which tells us about what minerals are exposed, we can say that there's this general trend on Mars where it goes from kind of phyllosilicate bearing rocks around up to about 3.5 billion years ago to kind of a lot of thick deposits of salts. We're mostly thinking of sulfates on Mars. There are very few carbonates detected, almost none. And then, you get to the last 3 billion years of mostly aeolian erosion. So from this, we knew that Mars kind of had, the surface of Mars is a good record of kind of surface processes at this time we're interested in around the origin of life. But there's another key step that we need to actually investigate those. And that's, as we look at Mars today, it's dry, barren, as I said. Oops, going the wrong way. Here we go. There's the Viking image of Mars surface. This was the first true color image of the surface, right? And so we realized it's dusty, it's covered in craters, there's ice at the 2 poles. And as we got higher resolution imagery and looked closely at these images, we realized, okay, there's a lot of evidence for water flowing across the surface. And that's both in kind of large flood canals or channels like these ones, and in kind of smaller dendritic valley networks that are much more similar to precipitation-fed valley network on Earth. And so there was water flowing across the surface. It looks like Earth. The problem is, without plate tectonics, how do we know what happened? How do we actually expose and read the sedimentary rock record if we don't have plate tectonics? And we actually weren't sure. So we got these images, in the 1970s. Some of these are actually higher resolution, they came later, but it actually wasn't until the year 2000 that we started to really be able to consider using Mars to read this whole sedimentary record. And around then there was kind of a critical paper, and it looked at this crater here. So this larger crater is called Holden crater. The smaller one outlined in gray, that's a boulder because the ejecta from Holden overlaps into it, is called Eberswalde crater. And both of these are part of a system that was connected by channels. So we know that channels came in, filled up Holden crater, channels came out just out of the screen, came back around. There's actually a channel flowing in right here, and I'm going to zoom in on the white box, right where the channel enters this ancient crater. And what we see is this beautiful inverted delta deposit. So as the river entered into this crater, it was carrying a lot of sediment. It was entering into a lake. And as it hit the lake, it lost the ability to carry so much sediment, and that sediment was deposited in these kind of delta lobes, where you can actually see kind of the avulsing and the different lobes of the delta as the water was depositing its sediment as it came into that lake. And this is actually exposed in inverted topography. So when the rivers were coming in, the rivers were low points, just like on Earth, right? They're the channels. So that's where the river's kind of coming down in. But now you can see that those are actually the high points, and they've kind of got cliffs around them. And so the reason that this delta deposit was exposed is because of the wind. And so over the last 3 billion years on Mars, you've had that wind kind of motivated or inspired by the really large temperature differences between night and day or light and shadow. And it's moving around, and it'll actually clear out rock in some areas of the planet. And so in this case, it cleared out basically the mud rock that was all around these channels, and left this kind of beautiful available stratigraphy where we could land a rover and drive up through and actually investigate the different layers of rock that were carried down into this lake. And so once this paper came out in the year 2000, that's when we realized, okay, Mars is a place where we can investigate a sedimentary record, where we can put together this story of, what was happening on Earth and Mars at this time before life. And that helps us address kind of a number of different questions, because sedimentary record kind of holds so much history, right? And so the way that we think about the sedimentary units that we see in my group is to split them up into this source to sink framework. It's some version of the sedimentary cycle, right? But the key question when you find a sedimentary rock is, what was the provenance? Can we tell anything about where this rock came from, what the igneous compositions were, what the volcanoes were like? How much was it weathered? How much of that was physical weathering or chemical weathering? Can we distinguish between those and think about how those happen during transport, which also causes mixing and sorting of sediments? Some alteration can happen due to weathering during transport. And then what happened after the sediments were actually in the basin or in the river or in the lake and deposited and potentially interacted with some kind of groundwater in order to cement them into a sedimentary rock that we're investigating. And then frequently they're altered. And actually, we've just been looking into possible sedimentary recycling on Mars. The Mars sedimentary cycle is definitely less evolved than the terrestrial one, but there are cases where we do see sedimentary rock recycling. Okay, and so just to kind of pull together a lot of that introduction, why do we care about these rocks? They give us that record of surface processes that's older than similar records on Earth and better preserved. They give us conditions at the time of formation of life or in the absence of life. And that's one where basically sometimes on Earth, we're so biased by, terrestrial conditions that we can't see processes that are happening or that would happen under, well, clearly it's very hard for us on Earth to see processes that would happen under a different gravitational field, under a different type of atmosphere, or without life being involved. And so Mars gives us this chance where for some processes on Earth, we've attributed them to life. And if they happen on Mars, then you kind of have to push back on that and say, well, maybe this happens abiotically and we've just only seen it with life involved on Earth. And so that kind of goes into that next bullet, but these different conditions force us to reevaluate our geological assumptions from looking at stratigraphy and sedimentology and rocks here on Earth. And as we've all learned during the pandemic, there's a lot of innovations that come from kind of interdisciplinary remote learning, stretching ourselves to think about this in a different way. And I just comment this little review article that we came out with earlier this year called Probing Space to Understand Earth. So like, how does this help us rethink our assumptions when we're thinking about any of the geological questions that we're typically thinking about on Earth? And hopefully for those of you who have come from totally terrestrial labs, there will be something to make you, in this talk, to make you think about how Mars observations might prompt you to think differently. Okay, so with this understanding that we have sedimentary rocks on Mars, that we have these kind of major environmental transitions through time, especially right around 3.5 billion years ago, around that transition from clay to salt to dry Mars, we found kind of one location on Mars. We also have a lot of constraints from engineering, and kind of the best place to land a rover tends to be the least interesting geologically, and vice versa, but we found a really good balance in Gale Crater. And so Gale Crater is about 110 miles across, or 155 kilometers across. And it formed around 3.7 or 3.8 billion years ago. The impact was strong enough to cause a central peak to form. So part of the middle of the rock actually rebounded up and created a central peak. It's an unusual central peak because it's actually as tall as the walls of the crater, which does occur in other locations, but is relatively rare. And the story of this crater appears to be that a lot of it filled up with sediment, and later the wind came back and actually eroded away a bunch of rock that had already formed. And so today we can actually see the effect of the wind blowing. So the wind is blowing in this way, and it's blowing this dark sand. It shows up the darkest thing on Mars because it's actively blowing, so it's not covered in the light tone dust that gets over everything, makes it called the red planet, right? So here's the dark sand. It's blowing around this central part of the crater, which is kind of stuck around the central peak, and it's actually blowing right out of the crater on the other side. That makes it deceptive. This crater is actually about 4.5, 5 kilometers deep. So this is actually quite a tall mountain. But because the wind has exposed kind of the sediments around the central peak in this long-term aeolian erosion, you can actually see in the layers right here, you actually get a record of what originally filled the crater. And in that stratigraphy, using spectroscopy from orbit, we're able to see kind of these major transitions. So that spectroscopy includes a layer where phyllosilicate clays show up really well, and then a thick deposit of sulfate salts, and then a large unconformity, which you can sort of see right along here. And above that, it's just kind of dusty and dry. So this is where we got to land. Thankfully, the area right next to the interesting rocks is flat. So it's ideal for a landing site. And we drove from actually pretty close to that kind of bullseye of, this was our aim to land here ellipse. And we landed pretty close to the bullseye and drove over to the sand dunes and up some of the layers. When we first landed, and we're kind of, I'm going to show you, the next image is from this traverse. It's from driving from that kind of bullseye over towards these layers making up the mountain. And so while we were on our way, we started seeing all of these fluvial sandstones, and some of these ones are highlighted are pebbly sandstones. So while this bottom of Gale Crater, this kind of moat around the central peak in Gale, was relatively flat and doesn't appear to have the same beautiful inverted topography delta that we saw in Eberswalde Crater, it turns out some of the same processes were acting here and were well preserved. And so this is one of the images, these are two of the images from the rover as it's driving. And this lower image is actually taken while the rover is sitting right over here on the right in the upper image. So if you sit right here and you look this way, which is towards the center part of the crater, you would see these rock layers exposed like this. If you look at the bottom image, you'll see that all of these these are pebbly sandstones, and they're dipping away from you. So you're kind of looking head on at a bunch of layers of rock that are kind of stacked up like cards in front of you. And from the side up here, you can see that those aren't just stacked like cards. They're not just flat layers, but in fact, there's kind of a little swoosh, right? And so these are actually cliniform layers in a delta where rivers were coming down and hitting a lake and dropping their sediment, just like we saw in Eberswalde. This time the topography doesn't show it off quite as well, but we can actually see these are from the rivers coming in, and then you come down and it kind of changes the shape right down here. You kind of flatten out, and you get that nice swoosh from the rivers starting to enter into the lake. So this would have been a lake that was 5 or 10 meters deep, right? These kind of, the edge of the lake is just a couple of meters for these cliniforms, but we know we're heading in the right direction. So we're coming in from the wall of the crater, we're following rivers in, and then they go down into the middle of the crater where there must have been a lake. And indeed, when we drove right over here, we found lake sediments. And so these are laminated lacustrine mudstones or siltstones. But you can see actually a dominant feature of these lake sediments has been that they're laminated. And so you can see kind of these little maybe varves, right? Varves has kind of an implication that they'd be annual. And in some cases, we think they might be event beds. So maybe whenever there's a storm on Mars, it pushes a bunch of sediment through and you get a nice layer of sediment. And then in between, maybe there's a little bit of precipitation from the lake. And that could cause some of these intervals, or maybe it's a seasonal trend or something along those lines. In either case, this lake slowly builds up in these nice laminations. Most of them are about millimeter thick, like over here. Every now and then you'll see them closer to centimeter thick, like this deposit. This lake was building up these mudstones for hundreds of meters of depth, right? And so we've actually measured 350 or 370 meters of mostly laminated mudstones. Every now and then we've seen a little bit of cross-setting, a little bit of wind came in, but for the most part, as we've been climbing up the mountain, we've been seeing a lot of mudstone. And so to give you a different perspective on this, this is the trail we took to climb up the mountain, and you see there's a little deviation here. We wanted to check out those dark sand dunes, and here's us climbing up. The star is closer to where, actually that star is off, sorry, we are over here now, just off this kind of jut of dark sand right here. But this is climbing uphill, and there's a nice ridge line right here. So from orbit, we had identified that these are the fluvial sediments. These are the river sediments. We drove across those to get across that flat, nice landing area to get to climbing up the mountain. And as we climbed up the mountain, we thought that there were going to be different layers, but instead that light blue is all essentially laminated mudstone. The orange and purple were highlighted because they look really different from orbit. The orange looks hematite rich and the purple looks clay rich. It does turn out that this is the highest hematite concentration we've seen, and this is the highest phyllosilicate clay composition we've seen. However, there's hematite and phyllosilicate clay in all of the samples we've taken in the blue mudstone. And so kind of our orbital detection may be biased towards probably large grain sizes, good textures for detection. But in general, this has been a really thick deposit of an ancient lake on Mars. And we haven't seen, I mean, there's been a couple of layers with some salt, but we haven't seen a strongly playa-like, a very evaporitic layer. Instead, it looks like this lake was pretty steady. You know, presumably it dried up. Presumably there were a couple of intervals. But for the most part, I mean, this amount of sediment, you're thinking on the order of millions of years of deposition of a lake that would have been active on Mars. And so this is really pushing us to kind of rethink early Mars in terms of how habitable it was and how long those environments would have lasted. Okay, I'm going to do a quick summary of the geologic history. I have this nice video from NASA. So here you're 4 billion years ago, 3.7, you get the giant impactor. You create the central peak. Again, Gale crater is about 4 or 5 kilometers tall. After you've created the central peak, there's probably some groundwater, but importantly, there's water that comes in from the surface off the edge of the crater. And that water carries conglomerates. We've got conglomerates, sandstones, and mudstones. And there's this lake that probably lasted for a really long time, just kind of steady mudstone deposition. Eventually you get up to that unconformity. Above a certain level, we don't think this whole thing filled with water. Instead, it's probably wind-blown sand, windblown sediment that filled up a lot of the crater, but probably turned a lot of it to rock. Then the wind changed sometime on Mars and actually started evacuating out the rock that had formed in the crater. And so that not only evacuated the Aeolian sandstone, it also evacuated the laminated mudstone, sandstone, and conglomerates. At some point, you have multiple intervals of groundwater interacting with the sediments and filling fractures. And then you get to 2012, and our little rover appears on the surface to investigate these sediments and gets to climb up these exposed layers of river sandstones and mudstones. And one thing that's kind of interesting that's not really captured in this video is that this shape of the current mountain and this kind of evacuation process by the wind, it's really a foreign concept. It's actually weirder if you think about it more, that you filled up a cup with dirt and then the wind came in and was like, no, I'm going to empty out the middle here. But the fact that the wind eroded through here, it's actually happened, at least to some extent, more than once, because there is another layer of rock kind of pasted on top of some of these river and lake sediments. And that's an Aeolian sandstone. And so sometime after that first episode, the wind blew in more rocks and those were cemented into sandstones. And so, whoops. So here's an example of that sandstone. I have to bring that up because I'll describe it a little bit, or why it's helpful to us in a minute. But you can see that it's kind of a beautiful Aeolian sandstone. You've got great dune cross-bedding, really large scale here, and it's kind of just unconformably pasted on top of the lighter toned mudstone that we've been mostly traversing. So this is that laminated mudstone and that plateau of much later sandstone. Now, as we've been driving, we do periodically get those selfies, but more frequently, we're actually able to acquire a lot of geochemical and mineralogical information about the sediments. So while we're driving, we can kind of shoot the laser. That's a laser-induced breakdown spectroscopy instrument, ChemCam, and that'll give us kind of a semi-quantitative chemistry of 300 micron spot sizes. So here's an example of how that would kind of hit a rock, and we could get the chemistry of those spots. We also have an XRF and fluorescence-based spectrometer. That one's kind of on the end of the robotic arm, and so it takes a little more commitment. So if we're stopped at a place for a little while, then we can get out the arm and look down at the soil or at the rock close up. We'll get kind of a pretty good quantitative composition, like kind of bulk composition of the rock across a 1.5 centimeter spot. The catch is that it does include whatever dust is on the surface, and so it can be sensitive to the dust, but it gives us a closer approximation of a bulk composition. And then this one really helps us tease out specific minerals, especially when you've got larger grain sizes. Then every now and then, and really kind of rarely in some of the sediments, more often recently, we're able to drill into the soil or drill into the rock, excuse me. So we'll get drill holes that are on the order of 5 centimeters deep, and again, sort of penny size, 1.5 centimeters across. And with that drilled sample, we can put it in an XRD instrument, a small portable XRD or a small portable mass spec, and actually get kind of quantitative mineralogy and a sense for what volatiles are present in the rocks. And so we'll take that back, thinking about this kind of source to sink processes that my group is, and we'll show how we use these different data sets with each of the layers of rock, right? The river rocks coming in from the side of the crater, the mudstones making up that long-lived lake in the middle of the crater, and the late Aeolian sandstones kind of pasted on top. For the first part, I'll be using a lot of APXS data. So it's this kind of bulk chemistry of kind of penny-sized spots on each of those units. So first off, there are some easy ways to differentiate between the units. And one of the easiest, especially towards the base of the units, this doesn't include the hundreds of meters of mudstone, just the base of it, is that potassium is particularly high and variable. This is potassium versus elevation, which is just our proxy for stratigraphic height. So potassium in the river sediments is high and variable. This dotted line represents approximately the average potassium content of an average Mars crust. So it's high and variable in the river. It's subdued, but still high in the mudstone, which kind of makes sense. if your river is going into a lake, there's probably rivers from other watersheds also coming into that lake. And so your high variable potassium from this particular river might be kind of merging with regular potassium from other rivers to pull the average down in the lake. And then the Aeolian sediments came at some later time. And so they actually just reflect average potassium on Mars and don't appear to be sourced from the same high potassium source. To dig into these fluvial rocks a little bit, what kind of controls their chemistry and why is it so variable? One of the first things that we were challenged with is that as we've looked at these rocks, they actually have pretty close basaltic type compositions. And sometimes the grain size is hard to see. So I mentioned that this panorama shows some pebbly sandstones. Here's one of the pebbly sandstones. And here's a fine grained sandstone. You can see that you can see some grains here and measure their grain sizes, but it's actually kind of tricky to get really precise grain sizes for these. Some combination of the dust cover and the long-term aeolian abrasion of all the surfaces that causes them to kind of have difficult textures to read into. But I was thinking the grain size probably related to the chemistry. And so we binned the grain sizes into kind of coarse grained to really fine grained sandstones and down to kind of siltstones and mudstones. And if you kind of just bin the grain sizes of the rocks, we could say that if you go through that whole fluvial group, which is called the Bradbury Group, these are all the river rocks, and the coarsest grained rocks have more aluminum. Finest grained rocks have less aluminum. And that spreads a little bit significant. The finer grained rocks are around 8%. And you can see there's a significant difference between the coarsest grained rocks, which are closer to 15% aluminum. So we've got kind of high variability, but a close relationship with these binned grain sizes. And it's not just aluminum. So the coarsest grained rocks are enriched in aluminum, silicon, and sodium, whereas the finer grained rocks were much more enriched in iron, magnesium, titanium, chromium, right? A lot more mafic elements. So we kind of concluded, okay, these coarser grained rocks are more feldspathic and the finer grained rocks are more mafic. Oh, sorry, we've got different vocab for the river sediments in each of these, but it's just the river rocks that we're looking at. There's a few elements that don't trend with grain size, the most notable being potassium, which we looked at before, and I'll look at one more time, but potassium doesn't seem to be the major control on the composition. Instead, you can control a lot of the composition with these feldspathic versus mafic elements. And the rest of these seem to have traveled in water. Okay, so we took this kind of one step further and did kind of regression analysis to say, you know, what is that feldspathic end member? And the feldspathic end member is effectively 92 weight percent of silicic elements or felsic elements. And we can model it out as about 60% plagioclase and something like 25% potassium feldspar, something like 10% of still those mafic elements. So, sorry, there is like a storm coming in Houston, so I hope my noise isn't too bad here. But so we've got that kind of feldspathic end member nailed down. We can say, okay, you don't get all the way to that feldspathic end member, right? But for some reason, you can see a pretty clear mixing between mostly plagioclase and mostly mafic elements. Potassium being the outlier here. Potassium, this is actually potassium versus sodium, which gives you a little bit of a better sense of how potassium is ranging as you go up. You can see that there's a few spikes in potassium, and we interpret this as there being one kind of more potassium-rich input source to this one kind of provenance area that's potassium-rich, that's periodically kind of more dominant or less dominant in the watershed and what's actually being eroded into this river. And so if you look against elevation, you see this one spike in potassium, you're probably eroding from that potassium-rich area, or the potassium-rich area could be blowing in the wind and you have a little more wind input at that time. We tried, as we were driving through these rocks, you have to plan in advance when you're going to drill. So we had kind of found this great outcrop that we were going to drill at, and we thought that it would be standard and tell us all about the river rocks. We only drilled one of these river rocks. And it was actually this rock right here. You can see that that ended up not being a great, standard average rock. But what it did do for us was it told us that indeed the high potassium was coming from an igneous provenance. So it was actually igneous sanidine that was holding that really high potassium. And so there's periodic input of igneous sanidine. But if we go back to the major components, right, we've modeled this in a lot of different ways. And so 90% of the rocks in the river, there's kind of two key points here that I want to make. One of them is that as you go from the coarse rocks to the fine rocks, you go from having the equivalent of something like 70% plagioclase and potassium feldspar in the coarsest rocks to 30% plagioclase and potassium feldspar in the finest rocks. And the mafic component kind of makes up the difference. And so there's a really kind of strong trend where there's grain size sorting between plagioclase that's coarse and mafics that are fine. One other point I want to make here is the fact that we were able to model a series of sedimentary rocks as if they were made of only igneous components is actually, it's kind of weird. And so we modeled each of the rocks as if they were only made of olivine, high and low calcium pyroxene, plagioclase, feldspar, and then apatite. These were kind of to help balance it out, right? You need iron oxide for Mars. But we know that these are sedimentary rocks, and so they probably include some phyllosilicates, they probably include some weathering products and secondary minerals. The fact that they can be modeled as combinations of just primary igneous minerals tells us that this is actually a very cold environment where not much open system weathering has happened. We do know that these rocks are cemented, and so these are not exactly the components of the rocks, but it was probably really cold and is probably cemented without significant cation loss. Okay, so this is kind of a weird combination, but we can actually dig into both parts of it and see whether it's reasonable. Thankfully, we found one igneous rock, basically. Found a couple, one main igneous rock along our traverse. For the most part, we're looking at sedimentary rocks. But in this one conglomerate, we were able to find this kind of fist-sized igneous rock that had been carried downriver and into the crater. And we named it Harrison. It's about the size of your fist. And it shows us that the igneous rocks upstream of this conglomerate contained these long plagioclase lats, right? They contain these long plagioclase phenocrysts in a mafic ground mass. And so this was really exciting because it kind of supports the whole story, right? So you ended up breaking up rocks like this, where you've got these really coarse grained plagioclase. The coarse grained plagioclase ends up in the coarse grained river rocks, and the fine grained mafic ground mass ended up kind of traveling down and ends up in the finer grained river rocks. Now, the second part that's surprising is that, again, 90% of these river deposited, cemented, sedimentary rocks can be modeled as these transport segregated, so kind of segregated by mineral size, combinations of primary igneous minerals. So what does that actually mean for the weathering of this system? And so I'll kind of dig into this from three different aspects. One, what was the igneous provenance? What did it look like? Can we characterize it a little bit better? Two, how cold was it? Why wasn't there very much weathering of these sediments? And three, how did it become rock if we're mostly seeing igneous minerals? In fact, a lot of the debate early on was, are these sedimentary or igneous rocks, right? It becomes very hard to tell if the composition is completely reasonable for an igneous rock or a sedimentary rock made of igneous minerals. Okay, so step one, what was the igneous provenance? This I've been working on with my postdoc, Valerie Perret. And so we think about the different data sets that we have. One of them is the mineralogy of a couple of mudstone samples and that one sandstone that we sampled. The other one is laser spots across rocks like Harrison or across any of the rocks we've seen. We have those chem-cam lids that actually zap the rock, and periodically, especially when you find a rock like Harrison, you actually get the composition of one of the feldspar minerals or one of the plagioclase minerals in this case. right? And so, for example, 0.16 in this grid fit right in the middle of one of these plagioclase minerals. So if we combine the information we have from the mineralogical instrument, the XRD, and from getting crystal chemistry of specific spots with the laser, where the laser was actually able to hit plagioclase grains, which it hit a lot more plagioclase grains than any other mineral because the plagioclase grains are much larger, we can kind of come up with this array of what feldspars were produced somewhere in the igneous provenance. Now we can't say, we wouldn't say these are all from one lava flow, but what we can say is we found this range of plagioclase minerals. Can you make it with one magmatic pathway? Or do you need two? Or do you need three? And if you need two, how much can we constrain them? Well, it turns out largely because of the really high potassium sanidine, as well as some calcic, closer to calcic plagioclases down here, you do need two different magmatic evolution pathways, right? You need one of them to be alkaline and one of them to be kind of more thalliatic. But we can constrain the characteristics of both of them in a general way, right? The provenance for this area is likely to be more complex than having two kind of series of magmatic evolution pathways exactly present in the watershed and coming down. But we can start to constrain, like we need at least this type of process to happen on Mars for us to produce the range of plagioclase minerals that we found. So we can explain it with kind of two magmas. One of them is more anhydrous. This is the one that makes up the majority of the plagioclase minerals that are kind of the coarse sodic to calcic plagioclase minerals that we saw. And that one would be an anhydrous magma extracted at a relatively high degree of partial melting, greater than 21%. And you can actually constrain FMQ in this case to +1. For the second magma, we also need one to go down a more alkalic pathway. And so that one would be a hydrous magma extracted at a much lower degree of partial melting. And that's required because we don't actually see any quartz. These are all sort of basaltic-like. So this one's more of a trachyite. And that would have produced the high potassium sanidine. And so this is the one that would have kind of intermittently come into the same watershed or been maybe intermittently exposed in the watershed and added to our sediments. Okay, so we have some sense, this is as much as we can do to trap kind of what would that provenance be like. So now if we kind of understand where the igneous stuff is coming from, the next question is, how cold was it? How much did that weather as it was coming downstream? And one of our common ways to analyze temperature, or at least perhaps not temperature, but degree of weathering, is this ratio called the chemical index of alteration. And it's just basically a ratio of aluminum to cations that are labile, right, that are easily moved. So in that case, it's calcium, sodium, and potassium. And this has been used in hundreds of studies on Earth to show that we can actually calculate, weathering pathways. And it's a reasonable way to approximate the weathering of plagioclase and feldspar based on the loss of cations relative to aluminum. So you kind of move up this CIA chart as you go from unweathered basalt to kind of more evolved rocks, and then up to smectites, illites, or an aluminum smectite like kaolinite, or sorry, an aluminum phyllosilicate like kaolinite, which is totally weathered. There's one catch here. You're thinking about how these cations are lost relative to the aluminum. So if you were to have a secondary salt precipitated in the same rock, especially for a sedimentary rock, let's just take sodium chloride or calcium carbonate. Calcium carbonate is the typical one on Earth. So if you add calcium carbonate to a rock, then effectively you're increasing this CaO and your ratio is going to decrease. So it will appear less weathered if there's added cations. So what you usually do on Earth is you correct by actually looking at the sample and taking out the salts or dissolving them, taking out the salts so that you can actually just say, what's the ratio for the primary minerals? How have they eroded? On Mars, we don't have the data set to do that. And we don't even form calcium carbonate. Instead, we've got sulfates coming in. So we can't accurately correct the CIA values on Mars, which means that all of our approximations of weathering are minimums. Does that matter for the Gale rocks? Well, I just already overspoke. Almost all of our measurements, our average chemistry measurements, are going to be minimum weathering. However, we do have drilled samples. And now we have something like 20 drilled samples where we've actually gone through and drilled into it, and we've gotten that mineralogy that tells us what secondary minerals there are. And so in the cases, in these drilled and scooped samples, I went through and said, all right, how much of how much of the calcium or sodium or potassium is being added by secondary minerals? And how does that change our interpretation of weathering? Okay, so if we go over this plot, the left-hand axis is the CIA, or the Index of Alteration. These are just a variety of different samples, and they're in order of CIA, which I should adjust, but they're showing, okay, so any CIA value below about 40, it's unlikely that you're really seeing chemical weathering, right? That's basically within the realm of an unweathered basalt. 40 to 50 would be in the realm of an unweathered granite, but for a basalt, then maybe a little bit of weathering happened. If you're above 50, then you're pretty sure some weathering has happened, some real cation loss has occurred, and so you can start to see that trend. So what we're interested in here is how much does it change between our unweathered minimum estimate and our corrected estimate. And it changes a little bit. You'll go from chemical weathering unlikely in a few cases up to chemical weathering possible. But actually, it turns out our minimum estimates are not that bad. Maybe the CIA is artificially lowered by about 5 units because of those added minerals. But for the most part, this isn't too bad of an approximation. Within error, it's really close. So we're going to keep using that minimum amount of weathering on Mars. We can also do a minimum amount of weathering on Earth and compare to a bunch of places on Earth where we've seen weathering of basalts. And so my other postdoc, Dr. Thorpe, he's actually now the Mars sample return scientist at NASA JSC. But he was looking at some samples from Iceland, from Idaho, and then kind of literature compilation of places around Earth, and said, all right, well, what do the chemical index of alteration values look like in these different environments when you have just the initial weathering of basaltic volcanic rocks? And it turns out that the samples on Mars are actually slightly less weathered, but overlapping with sediments in Iceland. So it's got to be quite cold. And if we look over that entire weather compilation, or this compilation of kind of global locations where we have basaltic rocks that are being weathered in their kind of initial weathering stages, you're going straight from basalt to something else. It turns out the amount of change in the cations, this is all uncorrected, by the way, the amount of change in the cations correlates all right with the mean annual temperature of the location. And so Mars is these kind of gray bars here, but in general, for some of these two Martian mudstones that we picked out, these two sections of mudstone, we're seeing values that correspond to kind of Antarctica to Iceland. And so this is the first time we've been able to say something about the temperature, but basically because of the low degree of weathering, we're thinking the annual temperature in Gale crater was quite low. It could be up to, I think Iceland averages about 7 degrees, and Antarctica is -20. But the degree of weathering in these sediments, even though they're 3.5 billion years old, is equal to or less than the degree of weathering that happens downriver in Iceland from volcanic rocks. Okay, the last question is, how does it become sandstone? And for that, we're investigating, this is why we use these Aeolian sandstones, is that the Aeolian sandstone unit is the only unit for which we have a modern active analog on Mars. So we have the glowing sand dunes. So we're using the sand dune compositions. And right now we're investigating how reasonable it is to assume that the sand in the sand dunes could have a similar provenance to the sand in the sandstone. If it does, then the kind of mineralogy of the two samples that we took tells us that you go from something like a lot of amorphous, 1/3 amorphous material and quite a bit of olivine to a lot of iron oxides and less amorphous material. And so if we can make that assumption, then it's pretty reasonable to attribute the cementation to the dissolution of olivine and precipitation of iron oxides. We're still working on whether that's actually a reasonable assumption to make by looking at a lot of different aeolian sandstones around Mars. But that's kind of what we're trying to dig into right now. And that pulls us back to this whole source to sink framework. And I want to tell you about one other project we're digging into. Okay, we've just got a couple minutes. So we're going back to Iceland. We're hoping, COVID dependent, we're going back to Iceland. And so those original sediments were taken kind of as you got downstream and right into the lake. And we're using this as an ongoing analog now that we do think that it has pretty similar weathering properties and pretty similar initial volcanic compositions. Mars is more iron rich, but it gives us a sense for kind of the weathering trends, transport trends, and how we preserve paleoclimate in the sediments. And so we're hoping to go back to Iceland. We just got this funded to go look at sediment cores from one of these small lakes, as well as sediments kind of going downstream, and the composition of groundwater versus the composition of surface water, to try to understand whether there's signatures of groundwater and how paleoclimatic shifts are incorporated into kind of those signatures of groundwater versus surface water and sedimentological record in the lake cores. So we're excited to hopefully kind of continue on that. And of course, the other big thing is that Perseverance is on its way to Mars right now. And so hoping to get a whole new set of data from yet another delta on Mars, where we see a river entering a crater lake and depositing these beautiful delta sediments. And so Perseverance will go investigate those. We'll be using the data. Hopefully, I'm hoping to be on that mission. Whether I'm on the mission or not, I'll definitely be following it really closely and trying to get the data from these new sediments to kind of help us constrain and inspire further studies of analogous environments on Earth, and see how that weathering, how those early stages of weathering, early stages of lithification can tell us about the ancient systems on Mars. And so with that, I will wrap up. And just note that if there are any interested students or postdocs, please reach out. I'm recruiting for my lab, and everyone should follow along. We're really excited for the Mars landing on February 18th. Thanks.
Thank you so much, Kirsten. That was a fantastic and very interesting talk. Let's see if people have questions that they've been storing up. Okay, I see Mong Han has a question.
Hi, thank you so much for the talk. It was so interesting. I guess my main question is about the fluvial system on the planet. I just Googled it. So Gale crater is roughly 6 degrees south. So, and I know that in the past has been some true polar wanderers drifting, and then has been very maybe by 20 degrees in latitude. So I guess my question is, if you describe this as a cold system, and then this is already a low latitude, does that imply that in a bigger latitude, then it is even being colder, and that would prevent fluvial system to even initiate?
It's a really good question. Yeah, there are higher obliquity swings on Mars as well as true polar wander. However, so much of our challenge for Mars climate modeling is making anything on Mars warm enough to have liquid water, that really this discovery of this long-lasting lake is really kind of, it contradicts the climate models in a lot of ways, because the climate models have to deal with the faint young sun. So it's 75% or so as bright as it is today. Mars is further from the sun than Earth. So in order to have liquid water on the surface, you have to have twice the greenhouse effect on ancient Mars that we have on Earth today. And so it's actually really hard to get it warm enough for water. And if you have this long lasting lake, you're going to want it to be as close to the equator as you possibly can. So I think we're still thinking of it being close to the equator. one advantage you have, and maybe part of why we're really interested in this groundwater question, is that Gale crater is about 5 kilometers deep. And so just in terms of kind of adiabatic lapse rate, at least today on Mars, down at the base of Gale crater, you can be about 15 degrees warmer than on the outside of Gale crater. And so some of that might also help, or some groundwater influence where you're kind of pulling in some of this lower heat to try to keep your lake. But I think it definitely could have shifted. Oh, actually, one point that it definitely could be related to the wind shifting though. The fact that the wind shifted so dramatically to fill up the crater and then to evacuate it could definitely be related to something about obliquity or latitude changes over time. We think the lake would have been close to the equator.
Thank you.
Cool. Thanks, Munghan. So next question is from Grace.
Hi, I really like your talk, and I have 3 questions. You may mention that in the talk, but I didn't catch it. The first one is, I saw you have an estimate of redox state of one of the provenance magma. How did you estimate that value? And the second question would be, as the rover going through, passing through the layer of mudstone, would you be able to use, for example, some major element or trace element as a proxy for estimating the change of redox or temperature in order to evaluate the paleoclimate of Mars? And the third question would be, how will study this sedimentary system help us to gauge the habitability potential of Mars and help us to search signature of life on Mars? Because my research is about searching signature of life on Mars. Thank you.
Yeah, okay, great question. So the first one, I'm going to refer you to our paper that just came out, but it's Pyre et al. 2020. And that kind of goes through exactly how we constrained things like the FMQ, the percent of partial melting, kind of influence of fractional crystallization. I believe it has to do with the pyroxenes that we found with the XRD, but double check the paper to get that one for sure.
Thank you.
And then as we're going through, in terms of redox state, iron is a really good indicator. With the mass spec, we can also see different redox states of sulfur, and we also see kind of different sulfur elements, but we've been using iron as our main constraint on redox state because it varies between hematite, coarse-grained hematite, and magnetite. And so that's been kind of our record. And there's a paper, Hurwitz et al., where we interpreted that as potentially a redox stratified lake. So it's possible that the part of the lake that's closest to the photochemical activity happening in the atmosphere was more oxidized, and the part that was getting groundwater influence is more reduced. And that's sort of one of the other things that we're hoping to look at in Iceland. And so, yeah, we've been using iron as our main redox indicator, I think, as we've been kind of telling that story. Oh, the other redox indicator we've seen is manganese oxides in just a couple of fractures. And that pushes your redox really far to the oxidized side. So we're still trying to fully understand that influence. And finally, habitability. We're definitely looking a lot at the phyllosilicates for habitability and for really understanding kind of what the water was like. And we'll do a similar questions for Jezero crater for sure. And the advantage with Jezero crater and the Perseverance rover is that we'll be able to bring those samples back, which will allow us to do kind of a more thorough search for organics. That said, Curiosity's mass spec has done some searches for organics, and we just recently, a couple months ago, got to do our first kind of derivatization experiment with the mass spec. And so they're processing those results now, and hopefully those will come out in the next year or so.
Great, thank you.
Great, okay, the next question is from Karen.
Thank you. Great talk. One of my questions is about whether you can see any colluvial deposits or landslide related deposits that might be derived from movement of water saturated groundwater saturated sediments along the axis or the edges of the crater. I'd expect to see some degradation by those kinds of processes, and I wonder if that gets mixed up with the conglomerate, or if you see other units that indicate these hill slope related processes.
Yes, so it's interesting. We've seen, okay, so in the conglomerates that we saw in the fluvial section, for the most part, we could find rounded grains, and sometimes I just lost a word, but like lined up little round grains so that we could see that they were carried in by rovers. But we know that there were definitely landslide processes helping kind of move sediment from the walls of the crater down into the crater. And I don't think we fully understood all of the ways that that's affected it. And I kind of pulled this up. It's still a little bit small in this picture, but there's a couple of big channels that are actually cutting through parts of the layered part of the mound itself. And so we might be coming up on what could have been either a delta or landslide deposit. We're still approaching it, kind of right up in the layers just above where we are now. And so I think it definitely played a role. And there was one other part I wanted to mention. Oh, there have been a couple of kind of piles of rocks. And so, you know, as we've been going, we're trying to look mostly at the bedrock, but periodically you get some interesting float rocks. And those almost definitely have either come down in kind of landslide-like processes or impact processes somewhere else, because we found a couple of piles of rock where it looks like a human went around and collected random rocks they liked and put them in a pile, and it has nothing to do with the bedrock below it, you know? So we're attributing those to some kind of landslide or impact.
And since it is a cold climate, you can get something like solifluction lobes, perhaps. And sometimes they also look very imbricated. I've seen solifluction deposits that have very imbricated looking rocks in them as well, and they're not fluvial.
Yeah, interesting. Yeah, that could account for some of the conglomerates that we saw. We saw a few conglomerates right at the base of the mudstone and more out in the fluvial sediments. But it does seem they were consistent with the same source. They were kind of in that same geochemical.
Thank you.
Thanks, Karen. And our next question is Laurent.
Hey, Kirsten. Very nice presentation. I have two small questions, completely unrelated. The first one is, how far are you from that unconformity and to the Aeolian sediments? Is there any chance, or when might be the rover being able to reach this completely different time in Martian history for comparison? And I guess just for the other one, I was just wondering if the lake could have been maybe isolated by a layer of ice, like dust-covered ice, that would have been discussed at some point for the Northern Ocean. So I don't know if you have anything about this.
Both good questions. So the major unconformity, this unconformity that takes us from like water deposited sediments to the dry sediments, I don't think we'll reach.
Okay.
We in our strat column here, we're now in this clay unit and we're approaching the transition to sulfates, and we did do a lot of stratigraphy underneath. And again, those 300 meters underneath were actually enriched in phyllosilicates. So some of this is obscured by dust cover, but we're not going to make it all the way up here. And in terms of your second question, I am so curious about that. And we're always talking about it because, you know, a layer of ice would really help in terms of, it's odd that we had lakes in basaltic systems in cold climates, but we just didn't have any carbon dioxide, carbonate precipitating. You know, the atmosphere on Mars is 97% or something carbon dioxide today. So we think carbon dioxide would have been involved in that greenhouse effect, but then you would expect carbonates in these lake sediments. And so the ice cover could help with that. But in the sedimentology, we just haven't seen any really, and it's a little bit unsatisfying because, you know, not seeing a dropstone is maybe just looking at the wrong part of the rock. But having looked at 350 meters of laminated mudstone, we would have thought we would see some indicator of that ice cover, and we just haven't seen any. And so that's kind of where we stand.
Thank you.
Oh, thanks, Laurent. Right, last call for questions. Oh, Monghan.
Sorry, can I ask one more question?
Go for it.
So I remember a few years ago, I read a paper by Mike Lamb and his student Matthew something in Science. They found report marks were cross-bedding on Mars, indicating some like dense enough atmosphere. So I was wondering, would that provide enough greenhouse effect or something that, I guess my question is, does the co-environment you're talking about here, would that compatible with their finding?
Is that the large ripple?
Yeah, I'm pretty sure they found ripple marks and cross beddings, one of the craters. I don't remember which crater.
Yeah. So what they were looking at was actually the dark sand dunes. And so we deviated over to see them, and I'm trying to see if my
so it's the same crater.
It is the same crater.
Oh, okay.
And it's the windblown sand. And what they discovered was that the sand being blown by the wind on Mars. I'm trying to think, it doesn't look like I have a great. This one shows some of it. Well, you can imagine a sand dune on Earth has 10 centimeter ripples, and then 100-meter dunes. And if you look at a dune field on Earth, you see those two bed form wavelengths. And what we realized when we drove up to an active dune field on Mars was that on Mars, there's also a wavelength that's something like 1.5 meters and actually has sinuous crested ripples, which look just like subaqueous ripples do on Earth. And so we call them large ripples, but it was pretty unexpected because aeolian bed forms are pretty conformable to these two wavelengths. So we weren't sure what kind of process would lead to these large ripples. And right now there is sort of a raging debate about that. But my understanding is that there is, because of the lower atmospheric viscosity, there's kind of an extra hydrodynamic type aerodynamic wavelength that creates sinuous ripples that are just like hydrodynamic ripples on Earth. So it's much the same process. And if that same process occurs on Earth today, then the ripples formed would be about 10 centimeters. And so they would actually be obscured by the faster aeolian kind of sedimentation, the classic ripple saltation like formation mechanism. And so that's kind of one of the things I always think of when I say, our studies of Mars can help inform our understanding of basic physical processes on Earth, because that's one that we hadn't ever had any reason to investigate, because it turns out on Earth it's just obscured by a faster process. But on Mars, because the atmospheric viscosity is so low, these long wavelength aerodynamic bed forms form and are actually also preserved in the rock record. And so the other part of Mitsu's paper was saying that these are preserved in the rock record, and the complication is that they look like stream cross-bedding, because they're about 10 centimeter, they create this 10 centimeter cross stratification record. And so we have to be really careful when we're interpreting ancient rivers in the cross stratification on Mars, because ancient dunes can actually have a wavelength that looks like a river cross stratification. So it's kind of one of the things that has been a hot topic in a way that we think that Mars is actually telling us to think about physical processes in sedimentology a little bit differently.
I see.
But it is quite a debate right now.
Okay.
Thanks, Monghan. Okay, so with that, let's thank Kirsten again, and you guys should all do your virtual clapping. Thank you very, very much for coming to visit us.
Oh, thanks. It was fun. Thanks for